From a distance, our blue planet appears as a serene oasis, teeming with life, a vibrant jewel against the cosmic dark. Yet, this tranquil image belies a constant, fierce struggle unfolding just beyond our atmosphere. Earth is perpetually bombarded by an invisible, powerful force originating from the heart of our solar system. This relentless onslaught is the solar wind, a torrent of charged particles ejected by our sun at incredible speeds. If unchecked, this stellar breath would strip away our atmosphere, boil our oceans, and render Earth a barren, lifeless rock. Humanity would not exist, nor would any complex life forms we recognize. But Earth is not defenseless. We are protected by an extraordinary, invisible shield, the magnetosphere. This colossal magnetic bubble deflects and absorbs the worst of the solar fury, maintaining the delicate balance that allows life to thrive. Join us as we uncover the secrets of Earth's silent guardian. To understand our shield, we must first look to its source, the Sun. Our star is a colossal nuclear furnace, a vibrant sphere of plasma that fuels all life on Earth. While it provides the light and warmth essential for existence, it also generates the very force that poses an existential threat to our planet. At its core, the Sun converts hydrogen into helium through nuclear fusion, releasing immense amounts of energy. This energy radiates outwards, creating the incredible pressure and temperature that sustain our star. This fusion process is the engine driving everything from sunlight to the violent eruptions we witness. The solar wind itself originates in the Sun's outermost layer, the corona, a superheated, ethereal atmosphere extending millions of miles into space. The extreme temperatures here accelerate plasma particles to escape velocity, constantly streaming outwards in every direction, carrying the Sun's influence far beyond its visible surface. This solar wind isn't just empty space, it's a super-hot, electrically charged gas, a plasma predominantly composed of electrons, protons, and alpha particles. These particles rocket through space at speeds averaging 1 million miles per hour, carrying a formidable amount of kinetic energy and magnetic field lines with them. Without a powerful magnetic shield, planets are vulnerable. Take Mars, for example. Scientists believe that billions of years ago, Mars had a thicker atmosphere and perhaps even liquid water. But over eons, as its core cooled and its magnetic field weakened, the solar wind gradually stripped away its atmosphere. Today, Mars's thin atmosphere offers little protection, leaving its surface exposed to harsh radiation and temperature extremes. This stark contrast with Earth highlights the critical role of a planetary magnetic field in sustaining an atmosphere suitable for complex life. It's a cosmic lesson in planetary survival. Even closer to Earth, our own moon provides a chilling demonstration. Lacking both a substantial atmosphere and a global magnetic field, its surface is directly exposed to the full force of the solar wind and cosmic rays. Astronauts on the lunar surface would have been constantly bombarded by this high-energy radiation. So, how does Earth possess such a vital defense? The answer lies deep within our planet, nearly 3,000 kilometers below our feet. There, Earth's outer core, a vast ocean of molten iron and nickel, churns under immense pressure and heat, creating a dynamic system of convection currents. These colossal electrically conductive currents generate Earth's magnetic field through a process known as the geodynamo effect. Imagine a vast, self-sustaining generator continuously operating since the planet's formation. This rotating convective liquid metal is the engine that powers our planetary shield. Extending thousands of miles into space, this magnetic field creates a vast, protective bubble around our planet, the magnetosphere. While invisible to the naked eye, its influence shapes the space environment around Earth, constantly interacting with the incoming solar wind, creating a complex and dynamic boundary. When the charged particles of the solar wind encounter Earth's magnetic field, they are largely deflected. Much like a river diverting around a rock, the solar wind flows around the magnetosphere, protecting the atmosphere and surface from its harmful direct impact. This deflection is our first, crucial line of defense. The outermost boundary where the solar wind first feels Earth's magnetic field is called the bow shock. Here, the supersonic solar wind is abruptly slowed and heated, creating a turbulent region. It's a cosmic sonic boom, a critical transition zone where the energy of the solar wind begins to be absorbed and redirected. Just inside the bow shock lies the magnetopause, the actual boundary between the solar wind plasma and Earth's magnetic field. This is where the pressure from the solar wind is precisely balanced by the pressure of Earth's magnetic field. It's a dynamic, ever-shifting frontier, constantly adjusting to solar conditions. The region between the bow shock and the magnetopause is known as the magnetosheath. This turbulent area consists of solar wind plasma that has been slowed, heated, and compressed, but not yet fully deflected. It's a chaotic buffer zone, absorbing much of the initial impact before the magnetopause takes over. Not all particles are deflected. Some become trapped within two donut-shaped regions called the Van Allen radiation belts, deep within the magnetosphere. These belts act as a cosmic jail, capturing high-energy electrons and protons, preventing them from reaching the lower atmosphere and endangering satellites or astronauts. On the side of Earth facing away from the Sun, the magnetosphere stretches out into a long, comet-like tail called the magnetotail. This structure can extend for millions of miles, a vast region where magnetic field lines are stretched and reconnected, driving complex processes that influence space weather. The most visible and beautiful manifestation of this cosmic battle is the aurora, the mesmerizing light show often seen in the polar skies. These ethereal curtains of color are a direct result of solar wind particles interacting with Earth's magnetic field and upper atmosphere, a spectacular byproduct of our shield's work. As some charged particles from the solar wind get funneled along the magnetosphere's field lines towards the poles, they collide with atoms and molecules in Earth's upper atmosphere. These collisions excite the atmospheric gases, causing them to emit light, painting the sky with nature's most magnificent display. The magnetosphere is far from a static barrier. It's a dynamic, constantly changing system, pulsating and reconfiguring in response to the sun's activity. Scientists around the world continue to study its intricate processes, using satellites and ground-based observations to understand this essential, yet invisible, planetary guardian. The magnetosphere, while robust, isn't impenetrable. Its greatest challenge comes from powerful solar eruptions, flares and coronal mass ejections, CMEs. When these hurl energized particles and magnetic fields towards Earth, our invisible shield faces its ultimate test, leading to potentially dangerous geomagnetic storms. CMEs are colossal clouds of plasma and magnetic fields, billions of tons, ejected from the sun's corona at incredible speeds. Traveling up to millions of miles per hour, they can reach Earth in days or even hours. Their sheer scale and energy truly challenge our planet's defenses. When a CME's magnetic field aligns oppositely with Earth's magnetosphere, magnetic reconnection can occur. This fundamental change in magnetic topology allows solar wind particles to penetrate deep into our protective bubble. This process, sometimes with devastating effects, represents a critical vulnerability in our shield. This influx of energized particles doesn't just dissipate, it triggers substorms within the magnetosphere, releasing vast energy. Particles are funneled down Earth's magnetic field lines, particularly towards the poles, accelerating to incredible speeds. This creates the magnificent, visible auroras we cherish. History offers a stark reminder of these storms' power. In 1859, the Carrington event, the most powerful geomagnetic storm on record, caused widespread telegraph failures. Auroras were visible even at the equator, dramatically underscoring technology's vulnerability to such powerful natural phenomena. Today, our reliance on technology makes us far more susceptible. Geomagnetic storms induce powerful currents in long conductors like power lines. These geomagnetically induced currents, GICs, can overload transformers, potentially causing widespread blackouts. A severe storm could paralyze critical infrastructure, demanding proactive mitigation. Beyond ground infrastructure, thousands of satellites orbiting Earth are also at risk. Increased radiation from solar storms can damage sensitive electronics, corrupt data, or knock satellites offline. Communication, navigation, GPS, weather forecasting, and financial transactions depend on these vulnerable eyes in the sky. Astronauts in low Earth orbit or those venturing further face direct exposure to intensified radiation. While spacecraft offer shielding, intense solar events pose significant health risks, increased lifetime cancer risk, and acute radiation sickness. Protecting human explorers is a paramount concern for all space agencies. Despite decades of study, the precise mechanisms triggering solar flares and CMEs remain active research areas. Scientists believe they're linked to reconfiguring complex magnetic fields within the Sun's atmosphere. Predicting their timing, size, and trajectory remains an immense challenge. Understanding the source is crucial. The Sun's activity isn't constant. It follows an approximately 11-year cycle from low, solar minimum, to high, solar maximum. This period is characterized by increased sunspots, flares, and CMEs. We're currently heading towards a more active phase, heightening the urgency for improved space weather predictions. Space weather forecasting centers globally, like NOAA's Space Weather Prediction Center, continuously monitor the Sun. Using dedicated satellites, they provide crucial real-time data on solar flares, CMEs, and the solar wind, offering vital lead times for industries and governments to prepare. Missions like SOHO, Solar and Heliospheric Observatory, and STEREO, Solar Terrestrial Relations Observatory, have been instrumental. They provide unprecedented views of the Sun's atmosphere and track CMEs from multiple angles. This allows forecasters to estimate speed and direction, a critical first line of defense. Despite advanced tools, accurately predicting a CME's impact remains complex. Small variations in trajectory or magnetic orientation can drastically alter its effect on Earth. Scientists develop sophisticated models integrating multiple data sources, aiming to refine predictions from hours to potentially days. Earth's magnetic field isn't static. It's generated by the molten iron outer core constantly churning. Over geological timescales, poles can even flip entirely, though slowly. But even in shorter terms, its strength and configuration are subject to subtle, yet important, variations. One current anomaly is the South Atlantic anomaly, a region where Earth's magnetic field is significantly weaker. This allows charged particles to dip closer to the surface, posing increased risk to satellites. It reminds us that our shield has natural vulnerabilities that complicate space operations. To mitigate power grid impact, utility companies implement various strategies. These include monitoring equipment for GICs, developing procedures to reduce grid load during a storm, and investing in resilient transformer designs. Proactive measures are essential for safeguarding our energy infrastructure and preventing outages. For satellites, designers increasingly employ radiation hardening techniques using specialized materials and shielding. Building redundancy into satellite systems and rapid data backup protocols also help minimize damage and ensure continuity of vital space-based services during extreme solar events. Beyond the solar wind, the magnetosphere might interact with interstellar phenomena. While largely shielded by the heliosphere, extremely high-energy cosmic rays, perhaps from distant supernovae, can still penetrate. Scientists investigate if these cosmic visitors have subtle, long-term effects on Earth's magnetosphere or atmosphere. Amidst potential dangers, geomagnetic storms offer Earth's most breathtaking celestial display, the aurora borealis and australis. These vibrant curtains of light visibly manifest solar wind particles colliding with atoms in Earth's upper atmosphere, exciting them to emit light. They're a beautiful reminder of our planet's invisible battle. The aurora's color depends on the type of atom struck and altitude. Green, the most common, comes from oxygen at lower altitudes. Red auroras are also from oxygen, but higher up. Nitrogen collisions produce blue and purple hues. Each flicker tells a story of energy exchange. Scientists delve into Earth's past to understand the long-term behavior of the magnetosphere. By studying paleomagnetic records in ancient rocks, they reconstruct the strength and direction of Earth's magnetic field over millions of years, gaining insights into its cycles and past vulnerabilities. Looking to our planetary neighbor, Mars offers a cautionary tale. Once possessing a global magnetic field and thicker atmosphere, Mars lost its magnetosphere billions of years ago. Without this shield, the solar wind stripped much of its atmosphere, transforming it into the desolate desert we see today. Earth's continued existence of a robust, dynamic magnetosphere is incredible fortune for life as we know it. It's a continuous, silent war fought at our world's edge, shielding us from the sun's lethal radiation and preserving the atmosphere vital for our survival. Truly indispensable. Understanding and protecting against space weather is a global effort. Agencies and researchers worldwide collaborate, sharing data, models, and expertise. International satellite constellations and ground-based observatories form a unified network, emphasizing this invisible shield protects all humanity, demanding a collective response. Despite significant advancements, many mysteries persist. What conditions lead to the most extreme geomagnetic superstorms? Can we improve long-term solar activity predictions? How do other celestial bodies influence our magnetosphere? These questions drive the next generation of space scientists and missions. The invisible shield, Earth's silent battle in the solar wind, is a saga of protection, vulnerability, and continuous discovery. It's a testament to profound forces at play in our cosmic neighborhood and humanity's relentless efforts to understand and adapt. Our existence is linked to this unseen guardian. The Earth's magnetic field, often taken for granted, is a vibrant and dynamic entity. It's not a static shield, but a living system constantly adapting to the intense bombardment from the sun. This invisible guardian shapes our planet's destiny, enabling the conditions for life to flourish and evolve over billions of years. Its continuous interaction with the solar wind sculpts the magnetosphere, a vast bubble of magnetic force stretching far into space. This intricate dance protects our atmosphere from being stripped away, a fate that scientists believe befell Mars, transforming it from a potentially habitable world to the barren planet we see today. Understanding this constant cosmic battle is crucial for our future. From the gentle auroras to the powerful geomagnetic storms that can disrupt technology, the magnetosphere reveals its power. Predicting its behavior, especially during violent solar outbursts, is a critical area of ongoing research and international collaboration. For countless millennia, this shield has been instrumental in life's grand experiment. It has protected evolving organisms from harmful cosmic radiation, allowing complex life forms to emerge and thrive. The very fabric of our planet's biosphere is inextricably linked to the strength and resilience of its magnetic field. The implications extend beyond mere protection. Without this magnetic field, our planet might have lost its water, its atmosphere, and its chances for life as we know it. It's a silent, unseen force that has dictated the very trajectory of biological development, proving indispensable for humanity's existence. In our modern era, with an increasing reliance on satellites and power grids, the magnetosphere's influence is felt acutely. A severe solar storm could cripple our technological infrastructure, underscoring the urgency of space weather prediction and robust protection measures for our critical systems. Scientists and engineers globally are dedicated to monitoring and understanding this dynamic environment. Advanced spacecraft like NASA's MMS mission meticulously study the reconnection events within the magnetotail, providing vital data to improve our forecasting models and safeguard our increasingly interconnected world. Looking to the future, challenges remain. The Earth's magnetic field experiences natural fluctuations, including pole reversals over geological timescales. While not an immediate threat, scientists continue to study how a potentially weakening field might impact our protective shield and require further adaptation. The tale of Mars serves as a stark reminder. Its ancient magnetic field faded, leaving it vulnerable to the solar wind, which gradually eroded its once thicker atmosphere. This planetary lesson highlights the critical role of a magnetosphere in sustaining any planet's long-term habitability and atmospheric retention. Our quest to unravel the secrets of the invisible shield continues. New missions, advanced simulations, and international collaborations push the boundaries of our knowledge, offering deeper insights into the fundamental forces that govern our planetary environment and the cosmic neighborhood we inhabit. The magnetosphere isn't just a shield, it's a dynamic frontier, a vast region of space where Earth exerts its influence against the torrents of the sun. It's a testament to the incredible power of natural forces constantly defending our existence, silently and steadfastly, against the vacuum of space. Its complexity and sheer scale are awe-inspiring. From the tiny particles that carry its magnetic force to the colossal currents that encircle our planet, every aspect of this shield is a marvel of physics. It underscores the profound interconnectedness of our solar system and Earth's unique place within it. The invisible shield, Earth's silent battle in the solar wind, reveals a story of an extraordinary natural defense. It's a narrative of cosmic forces, planetary, resilience, and humanity's ceaseless endeavor to comprehend the fundamental mechanisms that allow our blue marble to thrive amidst a hostile cosmos. This documentary has journeyed through the intricate layers of our magnetosphere, from its fiery origins in the Earth's core to its outermost boundaries where it grapples with the solar wind. We've uncovered its vital role in protecting life, shaping climate, and safeguarding our technological future. It is a profound reminder of our planet's delicate balance and the powerful, often unseen forces that sustain us. Our existence is not a given, but a precious outcome of a cosmic ballet between the Earth's internal dynamo and the Sun's explosive energy, mediated by this incredible shield. May this understanding deepen our appreciation for our home planet and inspire further exploration into the mysteries that still lie beyond our current grasp. The magnetosphere is a continuous saga of discovery, beckoning us to look skyward with renewed curiosity and wonder about our cosmic guardian. Thank you for joining us on this journey through Earth's invisible shield. If you found this exploration fascinating, please consider supporting our channel. Don't forget to hit the like button, subscribe for more captivating documentaries about our universe, and share your thoughts in the comments below.